So in this video, we're going to provide a broad overview of the concepts of Chapter 5, the two most important of which are how to compute the center of gravity of an object and how to compute the centroid of an area or a wire. So let's ground our discussion in everything that we've went over in the course up until this point. So if you think back to the introductory lecture, we talked about the idea of a distributed force. So what does a distributed force mean? So if you go back to Chapter 2 and really everything that we've been doing up until now, we've described a force by three properties: its magnitude and direction, because it's a vector, along with its point of application. But it's a pretty windy day outside, and I can hear the wind actually blowing on the exterior wall of the house that I'm in. Now, question for you. If I had to go outside and I had to point to the exact point of application of the force that the wind is exerting on the house, which point would it be? Naturally, hopefully you see that that's an impossible task to do because that force is distributed over the entire surface area of the wall on which the wind is blowing. In a similar idea, if I were to rest this can of Diet Coke on my hand, I'm not going to do it because there's still fluid left in there, but imagine that it balanced perfectly. And I would ask yourself, point to the actual reaction force that my hand is exerting on that can of Diet Coke in order to counterbalance its weight and keep it in equilibrium. You would tell me there is no single equivalent point because that force is being distributed across the entire surface of contact between your hand and the can. And you would be correct. And the point of that discussion is to say that in real life, forces are often distributed over some finite spatial unit. Maybe it's an area, maybe it's a volume, maybe it's a line, maybe it's not even continuous. Maybe it's just some discrete set of points. However, we're going to see how to deal with both of those cases a little bit later on in this chapter. In addition, in Chapter 3, we spent a lot of time discussing the idea of an equivalent force couple system. And I don't really want to go over that again because it can get wordy, but the big idea is if you have a rigid body and you have a bunch of forces and couples acting upon it, which are going to tend to translate it and rotate it, we can always, for any point on the object, define an equivalent force couple system. We got the equivalent force by adding all the forces up, and we got the equivalent couple by computing the moment of each of the original forces about that point. And if we were to draw two free body diagrams of the original force system and the equivalent force couple system, what is the big ideal? The big ideal is that each of those two systems of forces and couples acting upon the body would have a tendency to induce the same motion on the body in both cases. So it's equivalent mechanically from an exterior point of view. So we're going to use these two concepts in order to replace distributed forces, or forces that vary across some finite geometrical region, a volume, or we're predominantly going to work with areas in this case, by a single equivalent force. And the idea would be that this single equivalent force is going to tend to induce the same motion on the body as the distributed force. So you kind of have an idea of how we're going to have to do that already based upon what you've learned from Chapter 3. We're going to set the magnitude of that equivalent force as basically the sum of that entire distributed force. But you ask yourself, well, how do you sum a distribution? Well, hopefully you've remembered back to the principles of calculus where if it's actually a continuous distribution, we're going to have to use the concepts of integration. If it's a discrete distribution, we're just going to use summation or tabular approach, as we'll see in some of the examples later in this chapter. That's how we get the magnitude. The question is, how do we get the point of application? Well, we're going to choose the point of application such that for the given magnitude, both the distribution and the single equivalent force induce the same rotation of the body. So when we think about distributed forces, the one that is most common for us in our daily lives is the idea of a weight of an object. Because if you think about some rigid body, you can always arbitrarily decompose it into little individual chunks. And each of those little individual chunks, like we see here, for those, hopefully everyone has seen the concepts of calculus before, I'm taking this arbitrary shaped three-dimensional object and I'm breaking into these small little cubes, and each cube has an infinitesimal direction along each of the three coordinate axes. So I could call this dimension dx, this dy, and its height dz. And if I take the product of those three things, it will give me the volume. And if I multiply by some assumption of density, I can get the weight. So the whole thing I want to emphasize here is I'm talking about just this little chunk of the body, and its weight, its magnitude at least, is denoted by d sub w, dw, not sub w, because each of these dimensions is supposed to be infinitesimal. So don't even worry about the infinitesimal thing for now. Just assume that I chunk this up into a bunch of little cubes. There's a cube there, there's a cube there, there's a cube there, and there's a cube there, and there's the cube there. And I wanted to replace this by a single equivalent force. How would I do it? Well, in order to get the magnitude of that single equivalent force, I would add up the weight of each of those little chunks. And that is the idea of determining the magnitude, as we said at the beginning there. But the question is, what is the point of application? And physically, what would it mean? Well, wherever I apply that single equivalent force of the weight, it would have to induce the same rotation about any arbitrary axes. And I can pick any ones I want, but the natural ones that we're going to pick are going to be the coordinate axes, X, Y, and Z, as the distribution of forces. And whatever that equivalent point is that we would put the weight of that object is, that is the center of gravity. So that's kind of the more complex mathematical definition. What does it mean practically? Well, if you have some kind of object where the weight is actually distributed, if you can put your finger under it and you can balance it, what you've done is you've found the center of gravity. Now, why do I say that? Well, if you put you've at least found the line of action of the center of gravity. Because if you can counterbalance the weight of that object by a single upward force, right, the reaction force that you're applying must be aligned with the weight of the underlying object. So from practice, you can kind of think of the center of gravity as the balancing point. From our analysis point of view, we'll think of the center of gravity as the point at which we actually apply the weight of the object, even though the weight of the object is distributed across an area, or in real life across a three-dimensional volume. So what is the centroid of an area? Well, first and foremost, know that we're going to compute centroids of an area using this concept of moments of an area about an axis. And we'll talk about how to do that a little bit later in this video and through the examples later on in the chapter. But know that we're going to see this variable Q a lot, and it's going to be easy to forget what the variable Q represents, but it represents the moment of an area about a particular axis. So we're going to compute it using that tool from calculus. And the easiest way to think about a centroid for now, the way that I would like you to think about it, is if you have some kind of two-dimensional area and it corresponds to an infinitesimally thin plate, if that plate is homogeneous, meaning that it has uniform density across its entire area, then the centroid corresponds to the center of gravity. So you can kind of think about it as kind of the center of an actual two-dimensional area or shape, but there is an equivalency to the center of gravity if that area represents an infinitesimally thin plate of uniform density. So let's just look a little bit here. I just wanted to show you how these principles are actually applied. So say that we have, this is talking about the center of gravity of a two-dimensional body, and how do we actually contribute it? Well, if we wanted to, and the formulation that we have here on the right is actually breaking up the plate into a bunch of little infinitesimal chunks. And each of those little infinitesimal chunks is located at some coordinates, say x1 and y1. And it has some small weight, say delta w sub 1. And if we were to want to define the equivalent force system corresponding to the center of gravity, we would have to put it at a point such that the moments of this single force, W, which is located at this point X bar and Y bar, and that's a common notation given for centers of gravities of shape, that the rotation that this weight exerts about the Y-axis is the same as the sum of the rotation of all of these individual little chunks. So that's all that this is saying here. If you notice, it's saying that the moment about the y-axis of the equivalent force couple system on the left. So if it's just a single equivalent force, the way that I would get the moment is I take the perpendicular distance from the y-axis, which is x bar, and I'd multiply by w. So x bar by w, this is the rotation of the single concentrated force, is equal to the sum of all the little rotations of the little chunks, which as you move this little chunk around, right, the value of x1 is going to change. So really a better way to write this in your text would be to sum from I equals 1 to n, and then it would be x sub I and then delta w sub I. However, we know that as the little chunks that we're breaking it into get infinitesimally small, that this summation will actually become a Riemann sum, and it will reduce to an actual integral. So all that we're doing is we're saying that in order to locate the center of gravity, we have to pick a point x bar and y bar such that the equivalent single force system has the same rotation about the y-axis and the same rotation about the x-axis. So that is a little bit of typo in your text. I'll change it before I type it. And key point here, you can use the same idea for a wire. And one thing I should have pointed out, as you can probably tell in the case of a wire, is the center of gravity isn't always actually on the shape itself, whether it's a plate or a wire. So imagine you have like some circular wire like this. Is there going to be a single point that you can put your finger under it to balance it? There's not. And that's because the center of gravity is right in the middle. Or imagine like an area that consists of a circle with a smaller circle cut out in the middle. You're never going to be able to balance that with a single point because the center of gravity would be right in the middle. in that portion of the plate that's been removed. So hopefully that makes sense to you. So how do you actually come up with this formulation of centroids and first moments of areas and lines about axes? Well, if you notice, all that they're doing here is they're setting this problem up the same way that they had in the previous slide. X bar times W, where W is assumed to be the entire weight of the object, is going to be the rotation of this object about the y-axis, or the moment about the y-axis. And they're not actually, I don't think they're showing it here. Well, again, it's over here on the right, so that is your X bar. So if we were to have not a single equivalent force system, but to distribute this into little chunks, we would obviously have to do an integration, just like we showed on the prior slide. All that they're doing here is they're saying, let's compute the weight of this area by assuming that it's an infinitesimally thin plate. So the way that I can get the weight of a homogeneous object is to take the density of the volume and multiply by the volume itself. So how do you get volume of an infinitesimally thin plate? You take the area and you multiply by the thickness. So that's all that is there. That is the thickness multiplied by the area would give you the infinitesimal volume of each chunk. And then if you multiply by gamma here, that would be the density. So this is just a way to rewrite the weight. And what they're showing you is that on both sides, the factor involving the density and the thickness is going to cancel. And if you have the formulation assuming that this plate is infinitesimally thin and has uniform density, that this equation and this equation are the same. So hopefully that makes sense to everyone there. And they're just giving you an additional formulation showing you that X bar A, which we would write as the moment of this single force about the y-axis. Another way to write it is just Q sub y. And remember that whenever you see Q's here, you want to think about the first moment of an area with respect to some axis. So this is the first moment of the area with respect to the y-axis because it's measuring rotation about the y-axis. This same approach would give you the first moment of the area about the x-axis. And the coordinates that you get, usually in practice, what we're going to see in the examples is we're solving for X bar and Y bar, and that's going to allow us to determine the centroid of an area. So that's what I meant in the initial slides, that centroid is just center of mass, is if we assume that the area that we're dealing with is infinitesimally thin and has uniform density. We can also use the same formulation for a line, which we'll see a little bit later on. So the one thing I wanted to kind of close this initial video with is that there's a lot of there's a natural relationship between symmetries of areas and volumes and their centroids, or of course their centers of gravity. And now I won't read these to you in order to bore you, in order to not bore you rather, since this video is already long and boring. But the key thing that you want to realize is if you look here, if you define symmetry about some line, and this gives you just the formal mathematical definitions for that, if I compute the moment of that area about that line of symmetry, it's going to be 0. In addition, if I can define a line of symmetry, the centroid is going to lie somewhere on that axis. If I just have one line, that's an infinite amount of points. However, if I can define 2 lines of symmetry, like I've done here, in this shape, what I will find is that the centroid rather, is at the intersection of the line of symmetry. So I'm sure you all know this already from prior mathematical background, but it's a line of symmetry if you can actually fold the area on that line and the 2 sides that you're folding together overlap perfectly. So notice whether you fold the area about a vertical line or about a line that goes from this lower diagonal up, d prime. In either case, when you fold, you get perfect overlap. So anytime you have a line of symmetry, the centroid is on that line. The moment about that line is 0. If you have 2 lines of symmetry, the centroid is at the point of intersection. And in addition, let me just make sure I covered this last part. An area is symmetric with respect to center O if for every element you have an equal area on each side. That's just showing for a shape where you have symmetry about 0.0. And anytime you have that sort of symmetry, all this is showing you is that the centroid or center of gravity, if we're assuming that it is a plate with uniform density and infinitely thin thickness, is going to be at that point of symmetry. So hopefully that gave you a little bit of understanding of what we're doing in this chapter. We're trying to take distributive forces, most commonly of which will be the actual weight of an object, and replace them with a single equivalent force. If we're talking about the distributive force being weight, the point at which we apply that single equivalent force is the center of gravity. We talked about how centroid and center of gravity are related, along with the definition of the first moment of areas about axes, which are just what we've already computed in the course previously.